Okay, welcome to Chem 130. I'm Dr. Fred. I'll be your instructor this semester. I hope everyone can hear me okay. I was having some technical problems earlier. So anyway, before we begin anything, let's go through some logistics here just to keep SEC happy. So I got my little list of students. If you will, in the chat, once I call your name, can you please type in your full name? That is record that you're here. Otherwise, I gotta drop you, and I don't want to do that. Okay. So once I call your name, type it in. We're good to go. So I got, and if I crush your name, my apologies. not trying to do that. Dalea Azrag, are you here? No. How about Emmy Clayton? Emmy, there you go. There, I got you. All right, I got two Catherines. This one's Catherine Duvall. Okay, good, thank you. And then a Catherine Douglas. Catherine Douglas, thank you. Okay, then I got Raul Garcia. Raul Garcia, no. Okay. Erica Hart. Erica Hart, got you. Thank you, Erica. How about Teresa Leonard? Okay, thank you. William Lindblad. William, thank you. How about Molly Martinez? Molly Martinez. There you go, thank you. Larissa Moreno. Interesting, okay. How about Kieran Nay? Kieran, there you go, I see your name there, thank you. Christina Parchcorn. Christina. Emily Ragsdale. Okay. Good. How about Rachel? Rachel, thank you. Kyla. Thank you. Vargas, Galilea. Okay. So I'm missing Azrag, Garcia, Moreno, Parchcorn, and Vargas. Did I miss anybody? All right, well, welcome to Chem 130 at SEC. What I'd like to do is first start off with a little bit of background about me, so you have an idea where I'm coming from with respect to chemistry. I tend to bring a little bit of a different way of teaching chemistry. I've been in industry, been in a number of different industries. So anyway, let me start off with my little background. Okay, let me share the screen with you. All right, so as I stated, I'm Dr. Fred, aka officially Frederick F. Duarte. Okay. I'm an Arizona boy, actually about an hour east of here. As you go drive up to Globe, Miami. I grew up in a little small town called Superior, Arizona, about 100 years ago. And anyway, about 100 years ago, I left, joined the military. I am an Air Force veteran, a Vietnam veteran. Ended up in Kansas City. and that's where all my children are at. But ended up in Kansas City. Uh, Started off as a business major. Now, here's the irony of this whole thing. Here I am teaching you chemistry. And my first chemistry class, I totally bombed. I got a flat out big solid F. I just blew it big time. I learned later on that chemistry is a difficult topic, but it doesn't have to be. It is presented in certain ways, okay? And so I transferred to, in my education, I went to a university called Avila University, which was run by Sisters of Carondelet. And they just opened my mind up to chemistry. Fell in love with chemistry big time. So I got my bachelor's of art degree from Avila University in Kansas City, Missouri. I continued and got my doctorate there in the Kansas City area, specifically the University of Missouri in Kansas City. And my area, my field of specific chemistry was organic chemistry. I was a type of chemist that we synthesize and make compounds, specifically organic compounds. Some of them had medicinal value, some did not. Okay, but anyway, after finishing that, I became a research scientist. I'm retired now, and my area of experience was in process and product improvement. So basically to go into a process, check it out, see how we can, make it better, okay? Make it more productive, make it, improve on it. So that was my field, okay? Now, once I retired, I decided to teach part-time, and I have been an adjunct instructor now for some time at Scottsdale. And also next semester, I'll be starting new at Chandler Gilbert. But prior to that, I was a former adjunct at GCC. That's where I actually got my start as an adjunct instructor at Glendale Community College. But I now live in Santan, and Glendale is way too far away for a commute. So I'm trying to find schools that are a bit closer to my home, and so I don't have so much of a commute. So prior to that, I also was an adjunct instructor, specifically not only for chemistry, but for mathematics, general algebra, and for general physics at Carrington College, where I taught dental hygiene students and respiratory therapy students and physical therapy students, okay, for those classes. So previous experience, I've been in the multiple industries. In the military, I did masonry work, cement, concrete cement work. I worked in construction for multiple years, but over the years, I also did customer service. I've worked in food and retail industry. I also, once I started doing my research and development, got into software programming, and also many years did some caregiving. I have 9 children, and I have 9 grandchildren, so got a full house. All right, so here's the deal about this summer class. As you all know, everything just gets amplified. And why is that? Simply because we're going to teach 16 weeks of chemistry, and we're going to do it in 8 weeks. So literally everything is like doubled up. So there's a lot of work involved here. You gotta really stay on top of things. You gotta really discipline yourself when it comes obviously to your goals of higher education. Okay, I'm here to help you to do as much as I can. And if you ever find in the position that you need help, do not hesitate to ask for help. There is nothing wrong with asking for help. Okay. This piece of paper that you're striving for will bring for you opportunities unimaginable. Growing up in a small town of Superior, Arizona, never in my life would I have thought that I would have been doing projects that making products and processes that were used throughout the world. And I couldn't have done it without that piece of paper. Okay. All right. So you need help, seek help. We, not only through me, but through our tutoring service that we have, which is right next to, pretty close to our lab. Okay, so you're the one responsible for your learning, and don't blame others. This is your education. So time management, very essential. Unfortunately, I wish there was a magical thing I could say, hey, this is how you do it. This is how you manage your time. Well, there isn't nothing magical. Okay. Like yourself, some of you are working right now. Some of you have families. And so you're trying to balance on multiple things, multiple balls up in the air. Okay. I fully understand. We went through the same thing. I worked when I was working through education. And so you got to find something that works for you so you can time management. I do know that don't get much sleep during that time period. Okay. And so find a way to manage your time. All right. So any questions right now up to this point? What I want to do next is I want to go into Canvas. Now, I opened up Canvas a few weeks ago early to give you time to jump ahead, given the fact that we're given our chemistry is going to be thrown at you in 8 weeks versus 16. So I hope you took advantage. I went in there and saw some of you, yes, took advantage of it and started looking at it. So first of all, point number one, everything you need is on the Canvas course. Let me share the Canvas course with you. In fact, let me see if I can. I want to click the student view because that's what you see. My view is a little bit different. Okay, so we have the Canvas course here. Okay, now obviously on the far left, you'll see these links, not the far left, but the second column, you'll see the home button, announcements, syllabus, and so forth. Obviously, you found the Zoom room. Okay. And then all of the Zoom discussions will be recorded. And so then once I record them, I will upload them to my YouTube channel. And there's a link here to give you that opportunity to go back and view them. So you have access to a couple of recordings. Okay, let me go through the first module. The course is broken up in modules. So the first one obviously is the welcome module. Okay, and then this is stuff. It gives you the syllabus. Talk about a lockdown browser. Now, the exams that would be given, except the final exam, which is in person, but the other exams, 1 through 5, are online. Okay, but in order to access those exams, you have to have the lockdown browser to access that. So here in the welcome module, there's a section there about the lockdown browser, where to download it, where to get it. If you used it before, then you have to do nothing. You're ready to roll. Okay, but if you've not used it before, you need to go through a process of checking and downloading it, which is the lockdown browser is not just any lockdown browser. It is a browser specifically made for the Maricopa community colleges. So make sure that you're downloading the correct one, because the other ones will not function. Okay. And if you're doing Apple and some other non-PC format systems or iPad and so forth, there's some information there on how to download what you need for that. So get that working. There is an extra credit to demonstrate that, yes, my lockdown browser is working. Once you got it downloaded, you got it functioning, go through the extra credit, answer the questions, you get 5 extra credit points. Okay. Tables to print right here in your welcome module. There are 2 tables to print that we're going to utilize immensely. Okay. Where are we at here? All right. One of the tables you need to print because you need to have access to it, especially when you're taking exams. And don't open it up as digital because the lockdown browser would think that you are going outside the exam. So print this out. It's the periodic table. The periodic table I'm showing you here has a multiple bits of information that we're going to utilize. I will refer to this periodic table a lot. Okay, we have some tables in there too that you're going to be utilizing. The other table is called the shapes table. And it is this table here that you're going to also have, you're going to utilize. Okay, and you have a table here down at the bottom left. Here is a shapes table that we're actually going to be able to put molecules together. The formula, from the formula determine a general formula that you see here in this first column. And then from the general formula, determine the molecular geometry and actually figure out the three-dimensional effect of the three-dimensional look of that compound. Okay, so we'll be referring to these tables quite a bit. So just go ahead and download them. We have quick access to it. All right, let's go back to the home. All right, now all the chapters that we're going to cover, chapters 1 through 16, are set up as modules. Now, within the module of, say, chapter 1, you'll see an overview of what that chapter is all about. You also have the table for that, chapter for that particular book. So you don't have to buy a book. Not necessary to buy a book. The information you need is here, but if you want to get a book, by all means, go ahead. More resources. You can never have enough resources, and that's fine. Okay, but your textbook is here for you in PDF format. Now, there are videos. Okay, these videos have been created by a colleague of mine, Dr. Kim Smith out of GCC, when she talks about this particular chapter topic. So you're going to have access to this video plus the video that I record. So to give you more information about that topic. Included in there is a worksheet, which if there's any problems we need to go over, there's a worksheet there with the key of problems over that particular chapter. And then you have online homework, okay? Included in also are the PowerPoint slides in PDF format that I utilize. Okay? And then in this particular case, I've added the activity lockdown browser because that one's due this week. So it's a quick check to make sure everything's working and it's up to par. Okay. So you can notice here you have all the chapters all broken up. Okay. Down at the end, you have a final exam section. Okay. Again, it's that lockdown browser in case you haven't done it, but there is a practice final exam. There's a key there. Okay. Then there's an evaluation that will be due at the end of the semester, evaluation of the course and myself. Now, all the PowerPoint slides, if you want them, they're listed right there for all the chapters. Okay. One of the chapters we're going to do not during the Zoom sessions, but in the lab itself, because the lab is related to the topic. So chapter 16, we're going to do way ahead before the end of the semester. Okay. All right. Now there is an exam. Let me call up the syllabus here. Okay. Well, I hope you took time to take a look at the syllabus, all the information you need given to you in that syllabus. I'm not going to go over all of it. It's there for you for your reading. Okay, so there are course competencies that I need to cover. These are areas of chemistry, about 37, different topics of chemistry that we're going to cover throughout the semester. Okay, the word about your textbook. Again, your textbook is provided for you. But if you need to get a textbook, you can get a free one. It's open resource, and there's a link for it if you want it. Okay. More information from school, streaming, video, audio, stuff like that. Some information concerning the Lockdown browser and what you need to do to get it working for you. If you're doing iPad, there's a link there to make sure you're able to download the correct browser. Okay. All right. Now, as I stated, for the Lockdown browser, it is specifically the one for the Maricopa schools. Okay. So don't download some other Lockdown browser because it will not function properly. All right, let's do a quick breakdown of what we're going to be doing. All right, so we're going to have, you're going to have, each chapter you can have homework, okay? So there's a total of 15 homework assignments online. Short question, of the 15 assignments, the 3 lowest scores will be dropped, okay? So those are dropped. The homework is worth a total of 15% of your overall grade. So these grades are weighted grades. All right, so homework is worth 15%. Now, nomenclature. This is a very special exam. It's all in itself. What that is, the SEC department has their own little requirement that they want their students to pass what is called a nomenclature test. What that is we have a whole chapter on that. What it is either you're given the formula, and from the formula give the name of the compound, or vice versa. So it's about 20 questions online. Okay, 20 questions online, and you need to pass. You need to get an 80% to pass that requirement. So anything less than 80%, Canvas shoots it back to 0. Now, the whole exam is worth 10% of your overall grade. It can, if you're on the border of a grade where you're trying to push up, that 10% can kick you up to that grade level you want to get to, or it can keep you down from reaching. So if you're in the middle of the grade scale, it may or may not have any effect. Okay, so some students have worked hard to get that 10% and get the highest grade they can get, and others have just done a couple of times and just look at that, and they were happy with what they got. But you need to have at least an 80% to get the credit. 80%, and you have unlimited attempts to finish that nomenclature exam. But much more on that as we progress. Okay. Lecture exams, there's 5 of them. They're worth a total of 35%. And then the final exam, which is comprehensive, is worth 15% of your overall grade. Okay. Experiments. Experiments are, there's 11 experiments plus not 2 lab exams. I got to update that. There's only 1, what we call practicum at the end. Okay, they are worth 25% of your overall grade. The scale that we utilize is slightly different than the standard 90-80. It's 88 to 100 is the A, 78 to less than 88, etc. It's given to you right there. Okay. All right, so there's the breakdown. The homework, lowest 3 get dropped, 15%. On 5 online lecture exams were 35%. The nomenclature exam, 10%. Comprehensive exam were 15%. And then the lab experiments, 25%, including the practicum. The practicum is basically a combination of all the experiments you did. And you may need to, the way it works is we're set up at different stations. You go to a particular station and just follow the instructions. Maybe you just got to read a measurement, take a measurement. Okay. All right. All right. So now, I should make a note here. There is a percentage, late percentage for these online experiments and so forth. Everything has a due date. Okay. Now let me restate this again. Everything has a due date, and once you pass that due date, what happens is there is a deduction of 5% per day until you reach the 50% mark. What that means is after, say, 10 days, you're at the 50% mark. That means that if that assignment was, say, worth 10 points, the maximum number of points you can get is 5 for that assignment when it's late, okay? And it also means that there's the last day of the semester, which I want to say at the top of my head is the 12th, you can still do your assignment that you missed, but it's going to have encompassed with it the lateness, right, of that deduction. Okay, we're getting more people coming in. That's good to know. So 5% per day until you reach the 50% mark, and then that reaches the maximum number of points for that assignment that is late. All right, attendance policy. Well, you know, I have options here, and attendance encompasses not only coming to the Zoom lecture, but obviously the lab. We don't have much latitude given the summer. We don't have latitude to make up labs, so it's important that you do attend the lab days, because we're not going to have an opportunity to do any makeup labs. Now, with respect to lecture, I'm not the type of instructor who's going to sit there and take roll every day and demand you be here, because this is your education. This is your responsibility. I'm here to help you. I will do my best to help you to achieve your goal of getting through this course so you can go on and continue with whatever education avenue you have selected. And so we're all adults here. This is your money. You're the customer. I'm offering the service. I'm here to help you. But I'm not going to sit here and tell you that you can't lead a horse to the trough and make him drink, as they say, right? Okay. But however, I do have options. So if there's missing assignments, you haven't shown that you at least did something online, then I do have the option to drop you, and I don't want to do that. Okay, I don't want to do that. So to keep up with the classes, assignments, and we'll be all good here. If you have any questions, feel free to jump in and say something. We have online tutoring, but also we have in-person tutoring. Okay, and with respect to me, I'm adjunct. I'm not required to have an office hour. But if you find yourself in a position that you do need additional help, then shoot me an email. We'll see what we can do. Maybe we can set up a Zoom or something. Okay. All right. There's a question there. The question is, Catherine, we will be reviewing the PowerPoints together during lecture lab. Are those our responsibility to do outside of scheduled class time? No, the PowerPoints are for, this is what I use when I lecture about the topic. And I made sure that you have a copy of that, because some people like to print those out and make notes as I go through. So totally up to you as far as going through them and keeping your notes on them. Some people just like to follow along on their own. So they're there for your additional resource. Okay. Now withdraw. Hopefully you don't need to do that. But I do know this, that if you at the end of the semester, as long as you don't take the final exam and you decide to withdraw, you can request one. There's a point in time where you can do it on your own, but then after that, I'm the only one that can submit a withdrawal. And I can do that. I don't have a problem with that. But you can't take the final exam if that's your your choice if you want to withdraw. Take withdrawals seriously because it can affect your multiple things. It can affect, obviously, if you're having financial support, that can affect that. I know as a veteran, I used to have the VA. Dropping a class can affect your benefits. So I just want you to be aware of that before you do go that route. Okay. All right. There's a lot of other information for you here. Now at the end is kind of I just updated this because I was told, I wasn't aware of this, but on June 19, it's a holiday. Okay, I missed it. So June 19 is a holiday. You got to listen right here. Oh. So there'll be obviously no lab. So I moved everything. So lab 5 now goes to that Wednesday rather than that Monday. That's Juneteenth, I think they call it, right? So I had to move all that. So everything's been updated now. You have the updated schedule. Starting on the week of the 12th, you see that Tuesday, which would be the 13th, will be your first online exam, and it will cover chapters 1 through 3. After that, you basically have an exam every week, okay, online exam. One of these I had to move again because of the Juneteenth. Most of them are due on Tuesday. But I think I moved 2 of them to Wednesday because of Juneteenth and because of July 4th. Okay, so they're just due the following day. And they're online. They'll be open up, the exams that are online will open about 7 in the morning, and they'll be available for you until 11:59. Okay, so you got plenty of time there to set your schedule. You know ahead of time when they're due, okay, and so you can adjust accordingly. All right, excuse me. And then let's see, the last day to turn in any missing assignments is obviously the last week, which would be looks like the 20th. Yep, the 20th. It's the last week to turn any of the assignments except the exams. Exams, it's a one-shot deal. Okay, exams are due that particular day. But I'm talking about the assignments and the labs. Now, makeup labs, we are hard pressed. I can't overemphasize this, to make up labs. So do your best to make sure you're there on the lab day so you can complete the labs, because we won't really have too much latitude at all to have a makeup lab day. All right. So, and finally, not finally, but the last item of importance is the final exam, which will be in person. Will be in the lab, and that will be on July 19th. Okay, that will be comprehensive, covering all the chapters except 16. Okay, except chapter 16, chapters 1 through 15. And that's about it. Any questions right now concerning your schedule? Okay, let me.
What were you saying about chapter 16?
Oh, chapter 16 won't be on the final exam. It will. We're going to do that pretty early, about the 3rd week in there. So the final exam, we just covered chapters 1 through 15.
Thank you.
Okay. All right. Let me go back to. Where'd it go? All right. All right. So let's very quickly go all the assignment button here. This is a breakdown of the assignments to help you out. these in-person upcoming assignments coming up for you. I have a calendar set up so you can at a glance look to see what is due. So what's coming up. So today you can see today's the 30th. Obviously nothing coming up. Tomorrow we'll have the lab, which brings me to the point. Tomorrow and only tomorrow, we're not going to start at 1:30. We'll start 30 minutes later. I have an appointment I need to attend at noon, and I might be a few minutes late. So we'll start the lab on at 2 o'clock rather than 1:30. Okay. Any questions about that? I mean, you're welcome to be there whatever time you want, but we won't start at 2 o'clock. And it's mostly a safety. It's an introduction to the lab. We're not going to be doing anything. You're gonna get some goggles, and then we're going to go over some safety issues about the lab and doing chemical work and what we cannot do. And then come Monday, next Monday, the 5th, we'll start actually doing some of the experiments. Okay. All right. Any questions? All right. Let me go back to the modules. I will send you. I will communicate obviously with Canvas email. So please use Canvas email. If you not use Canvas email, just look here to the left, click on the inbox, and I'm access denied because I'm in the student view, but you would not be denied access. Okay, in your screen. Okay, but this is where you send me an email if you want to converse with me, and this is important. Because the email, if you send me the email through my edu address, your email that pertains to your course will get lost in about 500 other emails, okay? Because I get email not only from GCC, now I'm getting it from Chandler Gilbert and SEC, and then a bunch of things through Maricopa, okay? I go through that thing, about every couple of days to try to clear it out. And I don't want your email to get lost in there. With respect to Canvas, none of that's going to happen, okay? Because I have direct access to my Canvas email through my both through my regular email and through my app for Canvas app. And that way, no questions will be lost. All right? So, all right, now, there are in the modules, the third module down is called Additional Chemistry Resources, okay? These are bits of simulations that we can utilize to help us grasp the concepts of some of the chemical concepts that we're going to talk about. So right now, just go in there, click on it, and play with these simulations so you get to know. We'll come back to them and hopefully help you to understand some of the things that we're going to be talking about down the road here. I've also added some additional external notes of information about chemistry, how to take notes, how to pass chemistry, things like that. This nomenclature has its own module. We will talk about the different types of nomenclature. Again, is the naming of chemical compounds. And so you have the test there, which consists of 20 questions. And those 20 questions are, they either give you the formula or they give you the name. And if you're given the formula, you're asked to give the name. And if you're given the name, you're asked to give the formula, okay? Now, I've added another resource here to help you with this nomenclature test. It's called StudyMate, okay? On the far left, if you click that, you will get the following. kind of create you can also use StudyMate for yourself. Let's continue to StudyMate. All right, now up here, here's a link in red. It's listed as nomenclature practice, okay? So if you click on that, what I've done is I uploaded, I don't know how many compounds, about 140 some compounds I uploaded. 143 actually that I uploaded to the site. So in this case, you can select Flipkart. So here you are given the name of the compound. So in this case is lead Roman numeral 4 hydroxide. And given the name, they're asking you to write the formula. So you write the formula, and then to check yourself, flip the card, and there's the formula. Now note that StudyMate does not support subscript. So what this means here, this 4, is really a subscript to show you that there are 4 OH groups around that parentheses. Okay. You can go on to the next one. Carbon dioxide is the name. You come up with the formula. Okay. All right. Or you can do a matching choice. I would only select the 2 that I would work with is either the flashcard or the matching. That's because the other choices you have here, some of these names have hyphens, some of them have Roman numerals or parentheses, and StudyMate doesn't recognize them and sets them up properly. But with the matching and flashcard, there's no problem. So the matching, what it does is you're given the name right here, and then you have a choice of the formula. And you select what the formula is, okay? Iodine, heptafluoride. Iodine, which has a symbol I, hepta, which is the prefix for 7, and fluoride has a symbol F, so that would be the formula, okay? And this is a good source to help you prepare for that nomenclature exam. Okay, now what's going to happen with the nomenclature exam? Right now, the way Canvas, if you're not familiar with this, Canvas does not take it in your overall grade, does not take into account any ungraded assignments. So you haven't done an assignment, it doesn't know it's there, and you might be having a higher grade than you think. If you don't do an assignment, what I do after the due date, I put a 0 in there, and you can see the effect of that 0, okay? Well, even though the nomenclature exam, I repeat this, even though the nomenclature exam is not due until the end of the semester, please don't wait until the end of the semester to attempt it, okay? Because about halfway through the semester, I will put a 0 in there, so you can see what your grade truly is, because Canvas does not think, without that grade, it doesn't take that into account into your overall grade. What was happening in the past was students would wait till like a week before the semester ended. And then they attempted to get that 80% mark, and they were having a challenge. Well, they happened to be right on the border. And they really worked hard in 1 week's time to try to get that past the border, and they couldn't do it within the time constraints. So to alleviate that problem is now I go about halfway through the semester, and then I put in a 0 so you can actually see what your true grade is with that 10% due to the nomenclature. And then you can see where your grade sits overall, okay? All right. Let's see this. Yes.
How many tries do we have on the test?
Unlimited. Unlimited. You can try as many times as you care, and it will keep the highest grade.
Okay, thank you.
Sure. Unlimited. In fact, I got somebody else coming. Those of you that came in late, okay, let me double check. I didn't get a chance here. Delia, Ezra, if you can type in the chat your full name, please. I saw you came in a little bit ago. Type in the chat your full name, please, to show that you're here. Azrag, did you? I haven't seen it. Dalaya? Okay, Christine, yeah, there you are. Christine, I see you there. Good. Who else? Okay, Vargas, okay. Marissa Moreno, were you here? Yes, good. We got almost everybody here, everybody here. How about Raul Garcia? Did you make it? Raul Garcia? Okay, and Dalea, did I pronounce that right? I need you to type your name in, please. Yeah, can you type? Yeah, I see you. You're here. Can you type your full name down so it's record that you're here? So I guess the only one, there you go. Thank you very much. So the only one missing is Garcia Raul. All right. All right. Any questions so far? Went over a lot of information. Any questions that you may have? Now, I know sitting down here and listening to me for 3 hours can be very challenging. So what I'm going to do when it comes to Zoom is like every hour, we got what, 2 hours, 3 hours and 20 minutes. We end up at 4:20. So approximately every hour we'll stop and take like a 10-minute break, stretch your legs out a little bit. What question, Rachel, what do we need to bring in to lab? Nothing. You don't need anything at all. It's going to be a pencil, a paper, and not paper, something to write with. Because you'll be given everything will be given to you. You got all your textbooks. You'll have your lab manual. Okay, it's already been printed for you. That lab manual, we're going to go over it tomorrow. And then we're going to go over the safety. The first one is safety, and very straightforward. And let me see what else. Now there'll be nothing to bring.
Did you say that we're going to be getting the hard copies of the labs?
Yes. The labs will be given to you. I sent you a digital copy to give you time to take a look at them. But
Yes.
the hard copy will be printed out for you, so you don't have to get anything.
All right, thank you.
Sure, you're welcome. Larissa, is it possible to join from iPad? Yeah, I don't see why it wouldn't allow you to join. Do you have Zoom, Larissa? The Zoom app on the iPad?
Yes, I have it on my iPad. It's just a little difficult to see you because the screen is so tiny on my phone. But it says that it's trying to join. I tried to join through the app. It didn't allow me to do it once I clicked launch meeting. So I use a link and it says start video, but there's just like a little swirly loading circle. Well, I'm trying to join. Let's see. Can I flip this camera or how does this work?
I see fingernails.
Okay. Look at this. I see this here.
Okay. It sounds like your system. Are you on your Wi-Fi are acting up okay, or?
No, it's working perfectly fine. I'm able to hear you and see you on my phone. It's just not allowing me to log in through here.
Okay. That's a good question. Anybody out there also doing iPad? I'm not familiar with the iPad at all. I've not used it. So
I'm on an, oh, sorry.
Go ahead.
I'm on an iPad. It didn't have any problems for me. Have you just tried like leaving the web page and then going back though?
I've tried so many times, probably like 15 times, and it doesn't load. So I just figured I would try for my phone, and it worked with no problem for my phone. But it's a little frustrating because
I think I also know, are you going through like Safari or is it like the Zoom app or like what are you using?
so I have the Zoom app. When I click the link from Canvas and tap launch meeting, nothing happens. There's a link at the bottom that says having issues with Zoom client ?join from your browser. So I click browser, and that's when I'm seeing the little thing. Is there a meeting ID that you would be able to share with me so I can join from my
Yes,
iPad? Okay.
let's do that. Let's do that. Let me, give me 1 second. And let me hunt it down here real quick.
Thank you.
Sure. All right. Maybe. Okay. I need to stop record. Okay. Back on there. Okay. So to answer the question again, do it at your leisure, whatever, however works for you. Like I said, some students just take one shot and leave it at that, and they're happy with that score. It's only about 10 points, about 10 questions and so forth. And some, like I said, take it now, do it early, wait until I'm done with that chapter, and then do the second attempt. Okay. All right. Any other questions? All right, so we have quite a bit of information coming at you. Let's take a short 10-minute, okay? And then we'll come back and I'm going to jump onto chapter 1. Okay, knock that out, probably get it done. And then maybe touch on chapter 2, all right? So let's take a 10-minute. I got 2:20, I call it 2:30, come back at 2:40. Okay. Well, before I begin with the chapters, are there any other questions concerning anything about the course and where you can find what you need to find? Resources? All right, like I said, the labs will be printed out for you, so you don't have to print that out. But it does, the digital file gives you kind of time to read ahead. All right, well, I tell you what, I'm going to continue and jump right in, and let's jump into chapter 1. Let me organize my screen here a little bit. Okay, chapter 1. Oh, you don't want the end of chapter 1. That was a quick one. I was going through it and I forgot to rewind it. Okay, here we go. Chapter 1, matter. Okay, well, chemistry. Let's first define what chemistry is all about. Chemistry is a study of, as shows here, the composition, structure, the properties, physical and chemical changes of matter. Okay, because what we know is that all matter is made up of atoms, and we're going to learn about these atoms and what these atoms are. They themselves are made up of smaller particles, and that's where we're going to stop it there, because even those particles are made up of even smaller particles. We're not going to go beyond this, beyond the the first set of particles, okay? So we're going to talk about the atoms. We're going to learn what they're made of, specifically these particles that we call the protons, the neutrons, and the electrons, okay? So for Chem 130, the only three particles we can concern ourselves with is a proton, neutron, and electron, which together make up the atomic mass for a particular atom. Now, we're also going to talk about chemical bonding and how atoms come together to form a bond. And that bond could be either something that they share with respect to electrons, is electrons are the ones that are actually forming bonds, or it could be a bond where it's very similar to two magnets where they attract each other, okay, because of their respective charge that they may have. Okay. We're going to talk about types of reactions. And you would think with the millions of different chemicals out there that there'll be just an infinite number of chemical reactions. But it turns out there's essentially only 6 different types of chemical reactions, some that we're familiar with on an everyday basis. I'll give you a good example, okay? Let's say you got an upset stomach, you got some acid reflux. What do? Yeah, let's say you got a little heartburn. What do you do to correct your heartburn? Any ideas? Yeah, let me see.
Take like Pepto-Bismol or something?
Yeah, exactly. Tums is another good example. Tums, yeah, because in your stomach is an acid, specifically hydrochloric acid. We're going to learn a lot about that guy. We carry that acid around us all the time. And so if you have a lot of acid production, yeah, you're going to get a lot of heartburn. And what do? You take Tums. Well, Tums is a base, what we call a base. So we get a base and an acid come together, they neutralize each other. So Pepto-Bismol, Tums, okay, they are reducing the acid content in your stomach and you're having what is called a neutralization reaction, okay, an acid-base reaction. Another classic example of a reaction that maybe you drove your car today. You know, your car uses gasoline fuel to burn. That is a combustion reaction. Or this past weekend, you were cooking with some propane gas, okay? That propane was burning. That's a combustion reaction. But we're going to learn about these type of reactions. There's like 4 more that we're going to learn about. Now, the periodic table. We're going to learn about the trends of the periodic table. We see a table and, that's what we see. We've got 118 elements. But we're going to be able to look at the element and we're going to figure out certain trends and determine, for example, element number 10 versus element number 50, which one is bigger. And we're going to know which one's bigger by its position on the periodic table, okay? Not necessary to memorize information like that. Yeah, you can memorize it, but it's really not necessary because you can see its position in your periodic table and look at the trends about a specific property and be able to determine, like, for example, which element is bigger than the other, okay? I just mentioned the different types of an acid and the base coming together. We're going to have a whole chapter on acids and bases, okay? And electrolytes. Now, electrolytes are nothing more than elements that have lost or gained electrons, okay? These electrons are just amazing subatomic particles. They are so tiny that we essentially give them 0 mass because they're so tiny, but yet the effect they have on the properties of everything is just mind-boggling. And one of the reasons I really got into chemistry was because of these crazy electrons and how they affect the properties of chemicals all around us, and just it's mind-boggling. So electrolytes, you may be familiar with them. You've been out working out, you're sweating, and you drink the bottle is labeled electrolytes, but you probably never thought, what exactly is an electrolyte? Well, an electrolyte is nothing more than an element that has either gained or lost an electron, okay, to give it a charge. Now, we drink electrolytes because our body needs these electrolytes to cause current and signals to go from point A to point B. So these electrolytes are extremely important. Okay. All right. Now there's a concept called the mole, which the first time I saw this, I'm like, mole? We're going to talk about mole here. No, it's the mole. And it's an interesting concept because it confuses students, and it shouldn't confuse students because it's nothing more than a number. A number. It just so happens to be a very large number. We're going to have a whole bunch of information about that. But this particular, what happened to my, bear with me 1 second. I got a technical problem. My little, don't know. I lost my mouse. Okay, well, I guess I can't show it. Figure out what's going on. Anyway, the mole. The mole is nothing more but a number. Nothing, that's it. Okay. It just happens to be a very large number. In fact, when I say to you a dozen, we automatically think of 12. Okay. The name of a dozen is, well, the value of a dozen is 12. Well, the value of a mole happens to be a very big number. Let's see, my device says it's ready. Maybe it can work now. Bear with me for a second. My okay, well, not gonna happen. Okay, so going back to the mole, I have to fix this later. The mole is nothing but a number, but the number is humongous. It's so large that, for example, if you were to count that number at a rate of one number per second, 1, 2, 3, etc. By the time you get to the end of the number, it's going to take you a few thousand years. That's how large that is. Okay, but much more on that. Okay, then we're going to talk about this concept called stoichiometry. But you're already familiar with stoichiometry. You may not know it. For example, a car. Okay. Now, how many tires does a car need to roll properly on a vehicle? Obviously, 4 tires, right? So the stoichiometry, the relationship between the tires and the car is a 4 to 1. If you had a tricycle, the frame, the stoichiometry between the tires and the frame be 3-to-1. A bicycle, 2-to-1, etc. We'll find that in chemical reactions, there is a stoichiometry. Most of the time, we have reactant A, one reactant reacts with B to give us whatever products. It's a 1-to-1 stoichiometry. Occasionally, it's a 2-to-3 or a 1-to-3 or any other combination. But we're going to learn about the stoichiometry. We're going to learn how to determine what that number is, because it's very important when it comes to doing calculations. Okay? Intermolecular forces. Very important concept with respect to how molecules interact with each other. Okay? Which is related back to the electrons. Now, bear in mind that these electrons are on the outside of the molecule, and they're the ones that have an effect of what's going on with respect to the properties of that molecule. So these intermolecular forces, these are forces that molecules interacting with each other, have a big effect on the physical property. So for example, you have a cup of honey and a cup of water. And if I were to take that cup and then flip them over, obviously the water is going to win the race as far as emptying, okay? All right, let me stop for a second. There's a, where did it go? All right, move back. Okay, so, and these forces can be either very strong or very weak. Obviously, a cup of honey is going to take, as being more viscous, will take more time to empty, because the intermolecular forces of the honey molecules are much stronger than that of the water molecules. Okay, there's less interaction going on, and therefore, for the water, that is, and that's why the water flows a lot more readily. Then we're going to talk about solutions and gases. Okay. Now, there's different areas of chemistry. There's an area called inorganic chemistry that deals, something that normally doesn't pertain to carbon, hydrogen, and nitrogen. Okay. My field pertained a lot to carbon, hydrogen, and nitrogen, oxygen, organic chemistry. But then there's also an area called biochemistry that deals with the chemistry of life. Physical chemistry. This is an area where deals with the properties of chemicals. There are some chemists who get their doctorate in chemical education. And then there's environmental and analytical. These are, again, all chemists, but it's very specific, just like any other doctor or any other field, regardless of what field that you have your specialization. Okay, so chemistry is no different. Okay, there's a lot of overlap between the two, between all the branches, but it's because it boils down to chemistry. Now, chemistry, I would never say that chemistry is the most important thing in your life. It's not. But I will say that chemistry impacts every aspect of your life that you may or may not be aware of. Okay, everything that occurs around you, even internally in our body. All the chemical reactions, the breaking down of things we eat for lunch, those are all chemical processes, okay? Everything around us that we utilize, batteries, electricity, even clean water, energy, nuclear bombs, so forth, all of those deal with the chemical properties. Everything that we create, all the plastics and so forth, all of them deal with a chemical of some sort, someplace. So our impact, it's all around us, okay? Now, as scientists, we utilize what is called the scientific method, and you probably use it yourself without even knowing that you do. Okay, there's nothing magical about it. Okay, nothing magical. One, you make an observation. That's it. You observe something happen. Okay, for example, you may take a soda bottle and stuck it in the freezer, and come back a few hours later and opened the freezer door, and you made a big mess because the soda bottle exploded in the freezer. Okay, so that is your initial observation. So you think about it and you think, well, maybe the water, once it froze, expanded. Okay, maybe that's what's happening here. So you formulate a hypothesis, a best guess as to why that thing exploded. Okay, so then that's your hypothesis that ice expands when it freezes. Okay, so you go and research your hypothesis. One of the things is you go around and you start looking at the literature and see if anyone's done something similar, some type of research or reporting on this. You see what's out there. You gather all that information and you set up. You find that not much work is done out there. So now you set up a series of experiments. The 4-step. Okay, you might do different things. You might try different sodas. Right? You might try different types of sodas or different volumes. Just set up an experiment or different things and see what happens to them once you place them in the container. All right. Then you look at analyze your hypothesis after you've done all that, and maybe you might need to repeat some experiments as needed. Okay. And then after all that's done, you come to a conclusion based on your data. Okay, nothing more. Just based on your data, what is your conclusion as to what is going on? Water must be expanding when it freezes, and it does. In reality, it does do that. Okay. All right. In the lab, you're gonna be asked to do observations. You're gonna be asked to describe what you're doing. Okay, so it's quite imperative as a scientist and doing the labs, and not necessarily a scientist. Those of you that are, let's say, I know about half of you are probably in the nursing field. It's very imperative that you observe your patients. Because you are the forefront. You're the ones going to determine, what's going on with your patient. So observations, are very, very crucial. Okay, and being specific with respect to the observations. All right. So things like color. No color is colorless necessarily. Not clear. Okay, and clarity deals to, it's just a clear color solution or a clear, colorless solution, or is it cloudy? Or, okay, what state of the matter is it? Did it generate a gas? Is it a liquid? Is it a solid? Okay. All right. So matter is anything, I should say, that has mass. Okay? And that all matter is composed of atoms. Okay. So matter is anything that has mass. And all matter is composed of what we call atoms. Now, the concept of atoms is not new. It goes back to the Greek days of even earlier. Okay, but what these atoms are been made up of and how they behave relative to each other, that's relatively new. Okay, we have determined that the atoms are made up of what are called protons, electrons, and neutrons. And much more on that in a bit. Okay. Now, there are actually 4 states of matter, but we're only going to deal with the 3 states. The 4th state is plasma. And if you've ever seen the Northern Lights or pictures of the Northern Lights, you'll be looking at the 4th charged particles, which is plasma, which is the 4th state of matter. Now, we're going to deal with specifically solid, liquid, or gas. And we're going to be using diagrams to depict them. Now, if you look at the first diagram, solid, you see the solid here, you can see how the circles represent the atoms of whatever this chemical is, okay? And notice how ordered and structured they are relative to each other. That would represent a solid, okay? And if we were to take it a step further, and you can see how the ground spheres interact with each other, that interaction is what I mentioned earlier called intermolecular forces. Okay, those are the ones that change the properties of the solid. Now, if those forces are a little bit weaker, or we put temperature into the system, guess what? We break up those forces, and now we cause these molecules to separate from each other. And then now you're no longer in the nice ordered state. And now it's a little bit somewhat ordered, but there's movement. The atoms are moving relative to each other. Okay, and that's the middle diagram, and that represents the liquid state. Okay. And then finally, if you continue to put energy into the system, you actually break up those intermolecular forces even more so, where the molecules now are separated from each other because of the energy they gained, and they're separated from each other, and now they go into the gas phase. Okay. And so this diagram could represent solid, liquid, and gas. Okay. Water. Ice in the far left. There's very structured, very ordered. Put a little heat into the system, the ice starts to melt, and you get a liquid phase. And if you continue to heat that water now goes into the gas phase. Okay, so be familiar with these diagrams. We're going to use quite a bit of them, okay, to represent multiple things. But in this case here, these diagrams represent the three states of matter. Okay, so one of the properties of solids is as follows: that solids have a fixed shape and a fixed volume. So this little thing I have here, solid, okay, it's a fixed shape, okay, and it has a fixed volume, a volume that I can easily measure. This is more of a rectangle. I can measure length, width, and height, and that would give me the volume for that particular object, which is solid. Okay. The solids atoms are all ordered and structured as the previous diagram, and they will vibrate. Molecules have been shown that they vibrate even as they're sitting there. But because they're kind of frozen in position, they're not moving around, so they sit there and just vibrating in place. Okay. The solids tend to have a crystalline nature, but they can also have non-crystalline texture to it. Solids are not compressible. When we think about it, the solid atoms relative to each other are already as close as you can get them. So I cannot squish them together any further. Keep in mind that on the outside are the electrons that happen to have a negative charge. And if I have another molecule come next to it, it also has electrons on the outside, and they're negative charge. Well, charges of the same charges repel. So two negatives and two negatives repel, just like two magnets of the same, two north sides or two south sides, they repel each other, okay? And that's what's happening. They're being repelled from each other, and solids just won't compress because they're already as compressed as they can get. Okay. Now, most solids have a slightly higher density. What exactly is density? Well, kind of introducing it to you a little bit early, okay? And I give you the equation for it right there on the right-hand side in blue, where it says density is the ratio of the mass divided by the volume. All matter has density. You have density. You can go, if I were to figure out the density of this particular piece of solid, let's just assume there was more rectangular. Better yet, maybe it's my phone here, more rectangular, so I can measure length, width, and height and get a volume, okay? Length, width, and height gives me a volume. I can weigh this thing and now have a mass. So now I have a mass over volume, and I do the math, and I end up with a density of whatever grams per milliliter, okay? You can do the same for yourself. Everything has density, and you have a mass. Now, it might be a little more difficult is to determine the amount of volume because you're not a rectangle and you're not easily measured. But you can do what's called determine your volume by displacement. Think about it. Next time you're jumping in your jacuzzi, what happens to the water level? Any idea? You jump in your pool, you jumped in your bathtub, your jacuzzi, you're in there. Where's your volume level for that jacuzzi?
Sometimes the water can rise up when people
Is
get
that?
in.
Yeah, it will rise up, okay? Because you are displacing as you get into the jacuzzi or the bathtub or whatever, that volume's going to go up. Now, if you had a way to measure the volume before you jump in, figure out how much volume you have, and then you jump in the container and totally immerse yourself in that liquid, and you have somebody measure that the new height, that difference is that volume that you displace. And that volume represents your volume, okay? So now you have mass that you just go through a balance and weigh yourself. You have volume that you measured by displacement. That's what that's called, by displacement. You couldn't measure it directly like, this rectangular object, okay? So you measure it indirectly by displacement, and now you can calculate your particular density, okay? And you can calculate what your density would be based on your volume and based on your mass, okay? Now, most of the time, that solids have a higher density than their liquid state, and that the solids of those liquids tend to sink. The only exception is water. Water is very unique. And those of you who have lived in cold weather, I'm sure you have busted pipes, water pipes. And just like that example we just did for the scientific method, that you put a soda bottle in the freezer and it burst, okay? Well, it's because the water has this property that when it freezes, it actually expands. And so what's happening is if you take a unit amount of water, whatever, it could be any amount, okay, it will have a known density as a liquid. Okay, normally it has a density of 1 gram per milliliter. Okay. But if you take that same gram, that same quantity, and you freeze it, that 1 milliliter, that 1 gram of water now has a whole new volume. Instead of 1, it has maybe about 1.1. So now your ratio is 1 divided by 1.1, which when you do the math, you end up with a density of 0.9, which is less than 1. And that tells you that water, once it freezes, because it expands as it freezes, changes its volume of this density ratio, and therefore changes the density, okay? Changes the density. Think about this. Here's a little twister to get your brains kind of geared up. You got a loaf of bread, brand new loaf of bread, okay? All right, so it's rectangular shape, so you can go measure length, width, and height, and you got the mass. So now you have a density, okay? Now, take that same loaf of bread, don't open it, just keep it like that. Now take that bread and squish it as much as you can, in and down. Do you anticipate the density to change of that loaf of bread after you squished it, or would it remain the same? What do you guys think?
It'd be more.
It'd be greater, right? Because what's happening? Why would it be more? Correct. But why would it be more?
More compact.
More compact, which means look at the denominator of that ratio. Your volume gets smaller. That number in that denominator gets smaller. See what's happening mathematically? And so when that number in that denominator gets smaller, that means the density goes up. Okay, so the density goes up by compacting that loaf of bread. So it's a function of that mathematical ratio. We're going to use these ratios quite a bit. I'm going to bring them back over and over and over again because we're going to use that ratio quite a bit. And you're familiar with a lot of ratios all around us. You know, you're working right now, you're getting paid X dollar per hour. That's a ratio. You're driving in a vehicle, you're driving miles per hour. That's another ratio. We're going to talk about other ratios, grams per mole. That's another ratio. All right. It's foreign right now, but the concept of the ratio is consistent. And we can utilize that same concept when we start doing calculations. Okay. Anyway, solids, they don't mix because they're held in place. They're not going to move through diffusion or through osmosis. All right. With respect to liquids, liquids take on the shape of the container, but they have a constant volume. So if I take a gallon of milk in its regular container, there's its shape. But if I take that same gallon and I put it into a 55-gallon drum, does not the volume or the volume change? The shape, I should say? Yeah, because now I'm in this big container, 1 gallon of milk. It's more flat now, no longer the shape of the original 1 gallon container. But the volume is still the same, be it in a 55-gallon drum or be it in a regular milk container. 1 gallon is 1 gallon. Okay? Different liquids flow at different rates, depending on this IMF I talked about earlier called intramolecular forces, depending on how molecules interact with other molecules of that chemical. If they interact very tightly, then they're going to flow at a different rate, just like honey versus water, okay? Liquids are not compressible because just like the solids, there might be a little bit of compressibility, but not very much because the atoms themselves of that particular liquid are already close as to each other as they can get, okay? Which is a good property because if it wasn't for liquids not being compressible, you wouldn't have power steering, okay? You wouldn't have hydraulics, okay? Because of that, we're able to do power steering and power brakes and run heavy equipment. I have to have 20 people trying to turn the steering wheel. Okay. All right. So liquids have much higher densities than gases. Okay. Now, soluble liquids will mix uniformly. So here's something to might as well put in long-term memory. Like dissolves like, and you're already familiar with this. Italian dressing. How many of you guys like Italian dressing? Right? You have an oil layer and you have a water layer, an aqueous layer. They do not mix. They separate. You take that Italian dressing and just let it sit there. They're going to separate into the oil and the water. Okay. So like dissolves like because they differ because what we call the polarity. So polar things will dissolve in polar things. Right. So if they're soluble, liquids will mix uniformly together. Otherwise, they will not. Now, with respect to gases have no shape. They don't have no shape. They take on the shape of the container, just like liquids do. Okay. Gases can expand and compress. And why is that? Because the gas molecules relative to each other, relative to the liquid phase and the solid phase, are much further apart from each other. Okay, so there's a lot of space there they can collapse onto each other. So they can expand and they're compressible. Gases do not have a set volume. Okay. At this point, let me qualify this. At this point in Chem 130, gases do not have a set volume. We will learn down the road that only under certain conditions that gases will have a set volume. But for right now, no set volume. And they have very low densities, numbers much less than 1. And gases mix completely with other gases. The air around us is a mixture of nitrogen, oxygen, and carbon dioxide, and noble gases, and a bunch of other stuff. Oh, excuse me, I need to stop for a second. Apologies for that. Anyway, properties of gases. Gases will mix completely with other gases, so they are around us is a mixture of gases. Okay, gases do exert pressure because they're hitting the sides of the container. There's pressure. Case in point, your tire. Okay, you go in and you get a low tire. You go to Quick Trip and put some air in it. You're putting more matter into the tire, more gas molecules into the tire. Having more gas molecules in the tire, now more molecules are hitting the side of the tire, and the pressure goes up. Okay, so they do exert pressure. So when we look at solids, yes, have a fixed shape. Okay, and they have a fixed volume. With respect to liquids, no fixed shape. They fit the shape of whatever container that they have. And then with respect to volume, yes, they do have a fixed volume. And with respect to gases, and it's no on both questions, okay? Fixed shape and fixed volume at this point. They will have a volume in only certain conditions, but not right now. Okay, physical versus chemical properties. The main point about this concept is this. With respect to physical properties, okay, when they go from point A to point B, chemically, nothing has changed. It is still structurally the same chemical that you start off with. Okay, so when you take water, for example, and you freeze it as an ice cube, it's still H2O. As you add heat to that ice cube, it melts, becomes liquid, and it's still chemically H2O. Okay, and as you continue to heat it, and it becomes a gas, its molecule is still, the structure is still H2O. Okay, so physical changes, physical properties are things that the molecule itself doesn't do anything to chemically change their structure. Unlike chemical properties. The chemical properties of a chemical will completely change the structure. Okay, completely change the structure. So things like color, odor, taste, texture, melting point, that is the temperature that a compound will start to melt. Ice, for example, starts to melt at 0 degrees. 0 degrees, it goes from a solid to a liquid. Okay, that's called the melting point. The boiling point, for example, of water is 100 degrees Celsius. That's a temperature that, you're boiling water to make some spaghetti. That water is going to boil at 100 degrees Celsius or 212 Fahrenheit. Okay. Physical state, solid, liquid, or gas. We use the symbols lowercase s, L, or G in parentheses to show the physical state, be it a solid, be it a liquid, or be it a gas. The density is a physical property. Whether something is soluble in a particular solvent is a physical property of that chemical. Whether something conducts electricity. What happens, a lot of compounds, when you put them in solution, they break up into ions, and these ions are able to carry a current. Okay, so the hardness of a material is a physical property. Now, a chemical property is as follows. It could be that something is explosive, TNT, dynamite, very explosive. And in fact, once you ignite that, chemically, TNT no longer will be TNT when you're done with it. You have completely changed the chemical structure of that material. Sometimes some chemicals are very corrosive. It's their nature of the beast, or they're poisonous and toxic. But they may not do anything. There's a lot of chemicals out there that just sit there. They're inert. Nothing happens to them. Good example is gold. Gold is pretty inert. Okay, that's why gold can be as shiny as the day it was buried, thousands of years ago, and you dig it up and it's still as shiny. It's fairly inert. It takes a lot of work to get it to react. Or it's very reactive. Some chemicals just like coming out in the atmosphere, coming out here, they ignite spontaneously, it looks like. But they're reacting with the moisture around it and reacting, cause a reaction, okay? Or they rust or oxidize, or they just simply decompose. Okay. Now, these physical changes, I know you're well familiar with these, okay? I'm not giving you anything you don't already know. When you have a solid going to the liquid, what do you think, what is the name for a solid, the process of going from a solid to a liquid, what do you think we call that?
Melting.
Melting, solid to liquid, yep, okay. What about going from a liquid to a gas? What do you guys think? Liquid to a gas. Next time you boil some water to make some spaghetti, what do you think we call that?
Evaporating.
Yes, it can be.
Boiling?
Boiling is another one. All those are correct. So anytime you go from a liquid to a gas, whether you put energy into it, you want to boil water, you're boiling it. Or it can sit there and evaporate. You take a cup of water and put it in your kitchen countertop for a week or so, come back, water is mostly gone, okay? Because it evaporated. Oh, my dog. Sorry about that. He's back here now. So going from a gas to a liquid, we call that condensation. If you have a drink, okay, ice cold drink, humid day, on the outside, it starts to get liquid. And I always ask the question, well, where's this liquid coming from? Is this some Harry Potter magic going on? No, of course not, right? Out here, we have gas molecules. Obviously, we're in Arizona. And yeah, we have some humidity, but it's not like, being in Louisiana. I was stationed in Louisiana. Much even worse was Vietnam. It's very humid. Okay, a lot of humidity out here. All right, so we have the gas molecules of water out here, okay, a high energy state, and then they come and hit this container that's cold, and they transfer that energy from themselves in their gas phase onto the container, which is cold, okay? Because remember, energy always travels from high energy level to low, high to low, okay? Spontaneously. If you go the other direction, you got to put energy into the system. So you have high energy level. Think about it. You got a cup of coffee sitting there in your kitchen top, and you come back an hour later. Does it still remain hot? Of course not. It's cold because the energy of the hot coffee got displaced to the environment. Okay. And so here we come, high energy gas molecules hit the container, causes the molecules to come together and condense on the outside of the container here. Okay, so you have condensation. Okay, going from a liquid to a solid, straightforward freezing. Take some ice cubes, put them in the freezer. Okay, you got some ice cubes, right? Freezing. Now, this one you may not be familiar with. Okay, this is called solid to gas. So you're at a solid and it goes directly to the gas phase, bypassing the liquid phase very quickly. We call that sublimation. Sublimation. All right. Going from a gas to a solid, the reverse of solid to gas. We call that deposition. Let me give you some good examples of solid to gas. Dry ice, okay? Dry ice is a classic example of going from sublimation. Dry ice is nothing more than carbon dioxide, okay? Solid carbon dioxide. And it goes directly from a gas to solid to a gas. And then to make dry ice, you gotta reverse the process. You get carbon dioxide gas and run it through this little instrument, and you cause it to condense and form a solid, and you call that deposition. Okay. So next time you're at Fry's, you want some dry ice, pick it up. You might want to get some dry ice to your plants. Why would you do that? Why would you introduce dry ice to your plants? Any ideas? I wouldn't put them directly on your plant, but I would put them around your plant. Why would I introduce dry ice to my plants?
Takes longer to melt.
Not quite. Remember what I said, what is dry ice made of?
Carbon dioxide.
Carbon dioxide. There you go, Catherine. And what are plants like? Carbon dioxide. You got it. So giving them dry ice gives them carbon dioxide, makes them happy, and they in return give you oxygen. So clear up the environment a little bit. Okay. Or you can talk to them. Why would you talk to them? Other for psychological reasons. What are the gases that we exhibit is carbon dioxide. So talking to your plants helps the plants because they need carbon dioxide just like we need oxygen. All right, so with respect to physical changes, what we have here, I came back, I think I fixed it. Yeah, no, yes, it came back. All right. Okay, there's a question here. She sings to your plants. There you go, Larissa. Perfect. That's why her plants are happy. Not only is she hearing the music, she's got carbon dioxide going into her. Yep. All right. All right. So what we have here is a process, in this case, a physical process. Why? The question is why? Dr. Fred, how do I know it's a physical process? Okay. So in generic terms, what we do is something's going on here. I don't like I think I got to recalibrate my mouse here. It's kind of a weird thing. I got A, let me try over here. A plus B reacts to give us, let's say, C. This is a general reaction. Some chemical A plus some chemical B reacts to give us C. The arrow tells us it is some type of a process, okay? Going from the left to the right. That's generally how we write a physical or a chemical reaction, a physical process or a chemical process. All right, so here we have this arrow here, okay, which is telling us that we're taking H2O, all right? So this is formula for water, H2O. We all heard the term H2O. Well, here you go. Notice that 2 is a subscript. What it's telling you is there are 2 hydrogen atoms for every oxygen atom. And you take H2O, you run it through a process, and guess what? I still get H2O. I did not do anything chemically to H2O. It still remains H2O chemically. And I can verify that by looking at my physical state, because here my physical state in parentheses is the letter L, which tells me it's a liquid, okay? And then at the other end of the arrow is my physical state G, which tells me it's a gas. So what underwent here is a physical process of boiling. It went from a liquid to a gas, okay? And I deduced that just by looking at the formula I was given to the left of the arrow and looking at the formula to the right of the arrow. And notice that there's no change in the way the formula is written. And the only difference between left and right is the physical change. Okay. All right. So we're gonna have more to say about these physical changes here, but this here diagram kind of summarizes all the different steps of melting and freezing, boiling and condensing, and sublimation and deposition. Okay, and all this that you see, notice the spheres, the round circles are the same. Nothing has happened to them. They're still the same. Nothing chemically. These are all physical changes. All right, physical changes. And in the other aspect to take away from this is that notice that we're looking at the interaction between molecules, and I'm trying to draw the arrow here. You know, that when we put energy into the system, what we do is we break up that interaction between the molecules, causing them to go into a different interaction state, in this case, into the liquid. They're still somewhat ordered, but not as ordered as they were in the solid state, okay? And if we continue to put energy into the system, we break up that intermolecular force even more, so that now, if you look at the interaction between molecules, they're far apart from each other and gone into the gas phase. It is all about energy. And to go from left to right, we put energy into the system. To go from right to left, we take out energy. And by taking out energy from the system, we cause the molecules to come back together and condense onto themselves and start interacting with themselves even more so, to go back from the gas into the liquid, to eventually go back into the solid. So it's all about energy, nothing magical going on here, no Harry Potter stuff at all. Okay, more on physical changes. Atoms are always moving, even in the solid state. They continue to move. When you heat ice, for example, the water molecules gain energy. We call that kinetic energy specifically. That's energy of movement, because it's gonna, as the molecules gain this energy, those molecules want to move. Okay. Now think about it. You're on the hot beach. You're gonna go from point A to point B, go pick up a drink someplace, and you're barefoot. And the beach, the sand is hot. Now, do you think you're gonna nonchalant walk across that hot beach with no shoes on, or you're gonna sprint? You gotta sprint. You know, it's a little hot because you're picking up energy from the ground. That's what's happening here. Water particles are gaining kinetic energy. They tend to move faster. All right, and depending on how much energy they have or what it is, and at what point they gain it, it's going to drive them to go from the solid liquid to the gas. Okay, to demonstrate it here again in these diagrams. Okay, now let's talk about chemical changes. A little bit different now, okay? Chemical changes, the chemical composition is totally changed. The molecule is literally broken apart and rearranged to form something else, okay? The formula changes. We call these chemical reactions. Okay? The starting material, whatever it was, is destroyed, and now you create a new material. Different properties, totally different, completely. For example, let's do this. This is a classic general example of what we call a hydrocarbon. Hydrocarbon. carbon. Gotta figure out how to fix my pen here. Hydrocarbon is this species right here. It is a species made up of nothing but carbon and hydrogen. X represents some numbers, more on that down the road, okay? But when you drove your vehicle today, this is what you did. You're burning gasoline. So you took a hydrocarbon and in the presence of oxygen and a little ignition, boom, okay? You burnt that hydrocarbon up, a lot of energy given off, okay? And a lot of the energy is controlled, so you can run the front wheels if you've got front wheel drive and get you to where you need to get. One of the only two products, I think you might as well learn this one now. For this type of combustion reaction and for Chem 130, the only two products will generate, excuse my dog again. The only two products that you're going to generate are carbon dioxide and water, okay? Carbon dioxide and water. So sometimes, occasionally, you might see this, you're in traffic and you look at the car in front of you and you look at the tailpipe. And you see a liquid kind of oozing out of the tailpipe. What you're looking at is that moisture, that water has condensed and is falling out of the tailpipe, burning of the hydrocarbons, okay? So this is a combustion reaction. Notice something, the hydrocarbon has been changed completely structurally. It went from a hydrocarbon now to carbon dioxide and water. Okay. Classic example of a chemical change. And sometimes we have indicators of a chemical change. For example, something that burns, it's combustible, definitely a chemical change. Something that rusts. I used to have an old Ford, had a lot of chemical change in it, had a lot of rust. That's a good indication that a chemical process occurred. Bubbling occurs without heat. Good example of this would be Alka-Seltzer. If you ever look at the label, which is amazes me about Alka-Seltzer is this, that if you look at the label, yeah, way back when I wonder, what is fission in there? Turns out it's a bicarb and maybe some citric acid. So you put they put in the solid form some sodium bicarb, some citric acid. They put it in the solid form and compress it in that pellet so it doesn't react with each other until such time you dump it in water. And when that happens, the acid, the bicarb and the citric acid react, have an acid-base reaction to generate carbon dioxide, give you that fizzing going on. Okay. All right. So that's a good example that there's bubbles being given off without any heat. Okay. Or you may have two liquids that are solid, two liquids that are clear, colorless. And then the moment you mix them together and they get cloudy, you get what's called a precipitation. Okay. That itself is another type of reaction we're going to talk about eventually. Or it could give off heat. There are chemicals that you put together, they get pretty hot, very exothermic. Next time you're at the pharmacy, you want to buy a cold pack or an ice pack, a heat pack, you get the pack and you smack them. Chemicals intermix, that pack gets hot. You put that on your muscle and so forth. Or vice versa, it would get cold depending on which one you purchase. Or you have these chemicals that you can, these plastic, now I'm having a senior moment with the name of them, you just crack them and light is given off. You can hang them all over the place. See, it's a chemical reaction that's occurring and light is one of the products, okay? Or there's a change in color. Maybe you got a solution that both of them are clear, no color. Put them together, you get a nice blue color. That's a good indication a reaction occurred. Or you may have an odor, which can be either very nasty odor or very nice odor. There are chemicals that you put together that the chemicals themselves, by themselves, they'll smell terrible. But the moment you put them together to form a new compound, oh, it's very nice. a lot of like wintergreen, banana oil, these type of compounds are the result of two chemicals coming together and generating that type of reaction. Okay. So there's some indicators of a chemical reaction. Okay. Here's an example of a classic reaction. It's one of my favorite examples because we have sodium. Here's a symbol for Na. We're going to start learning symbols. Okay. So the symbol for Na is called sodium. This is sodium metal. Now, not to be mistaken with the sodium ion like in table salt. Sodium ion, totally different, okay? And the only difference between this sodium and the sodium you put on your French fry is guess what? One tiny little electron. Tiny little electron. And there's a vast difference in the properties of the two. Then you have over here chlorine gas, which is a poison. Okay, you have chlorine gas. You got sodium metal, which is extremely reactive. The moment you can Google this and you can look up sodium metal and creeks. You got guys out there dumping bricks of sodium metal into a river, and you can see a big old massive explosion occurring because there's so much heat and hydrogen gas that it just blows the hydrogen gas up. Anyway, sodium is very reactive with the atmosphere. Okay, very dangerous metal to work with. Chlorine gas, very poisonous gas to work with. Okay, when you put the two together, there's a reaction that proceeds, and you end up with, where'd it go? This material right here, NaCl2Cl, which is called sodium chloride. That you can put on your French fries. That's what you put on your food and your French fries, sodium chloride. Okay, so from a hazardous metal to reacting with a poisonous gas, you end up with a product that you can put on your French fries. Okay, and not really hurt you too bad unless you get high blood pressure. Okay. And the only difference between what happened here is we had a transfer of electrons going from the sodium to the chlorine. And to give you some perspective, it'd be like analogous to me, say, plucking one hair off and totally changing my personality to God knows what. Totally changing it. And such an effect, and that's one of the things that got me excited way back when about chemistry, because it's like, how do these electrons, how can they have such an effect on the properties around us? It's just mind-boggling. Okay. All right, so that's definitely a chemical process here. All right, so here you're being asked to look at the reaction, okay? Granted, this is day one of chemistry. You don't know what the formula is, you don't know anything, but I know you can look at this and deduce some information, okay? All right, process of elimination, process of breaking it down. I'm an advocate of looking at the problems that you have to solve and you break it down to pieces, steps, right? And 9 times out of 10, that works pretty well to go through that. All right, so let's take a look at number 1. Well, what do we see with respect to the formula that we're given? We have NH3 on the left side of the arrow. And if you look at the right side of the arrow, again, you have NH3. So what has happened is nothing's happened to the structure of NH3. I know you don't know what NH3 is, but I'm going to tell you here when we're done. Okay, because we're going to be using NH3 for multiple things down the road. So we have NH3, NH3. So nothing happened to it structurally, okay, chemically. It's got to be a physical change, okay? So I look at the physical properties and I see I start off with a gas, because parentheses G, and I end up with a liquid. So there you go. So all what happened was a physical change for this NH3, which, by the way, is the formula for ammonia. So you ever use some ammonia cleanser for your windows, smelling that ammonia, or you smelling the dirty diapers? That's what you're smelling. Okay, there's a formula for NH3. We'll come back to NH3. We're going to use that quite often for multiple things throughout the semester. Okay, so okay, no worries. If you have to, if you guys need to leave, no worries. Go ahead and leave. You're welcome. You know, after we're done, I will upload this, what we recorded. Hold on 1 second, and you can view it at a later date time. Okay, no worries. Guys, don't feel like you're trapped here, okay? If you have to leave, then so be it. All right. That said, I've recorded, I'm recording this. You can view it later on. All right, let's take a look at the second one. Again, we start off with NH3. Yeah, no worries, that'll work. Okay, so the first one is strictly a physical change. Okay. Second one, we continue with NH3, but there's a big difference this time. When we look at the right of the arrow, the key that there's a difference is that plus symbol. That tells us that we have at least two different products, okay? And when you see that plus symbol, that tells you that whatever you started off with over here must have been broken down to give us at least two different products. And in this case, N2 is called nitrogen gas, and H2 is called hydrogen gas, okay? Excuse me. And so that in itself, having the fact you got a pluses in the product side tells you automatically, should tell you that you have a chemical change, okay? Here's another one, H2O2. At first sight, you may think that's water, but it's not. Remember, water is H2O. This has two oxygens, okay? All right, again, don't know what it is, but what I do know just by analyzing the equation I'm given, that one, I got a plus symbol again, which tells me I got two different products, okay? Two different products means that I have a chemical change. Okay. That, by the way, H2O2, that is the formula for hydrogen peroxide. You ever use it to treat a cut or maybe to color hair or something? That's the formula for hydrogen peroxide, H2O2. Okay, again, we're number 4, we're utilizing hydrogen peroxide. But if you look at the product side, we still have H2O2. Nothing's changed, okay? And it's a solid. So chemically, hydrogen peroxide, H2O2, remains the same. So what must be occurring here is a physical process. Okay. And then the last one, again, you got C6H6 on the reactant side, and then the same thing as the product side. Again, I understand you don't know what that is, C6H6. Okay, but hopefully based on what we talked about earlier, you can recognize that we have hydrocarbon here because that molecule is made up of nothing but carbon and hydrogen, specifically 6 carbons and 6 hydrogens. All right, but the point is that nothing happens to the reactant. It's still C6H6 remains C6H6 as a product. So it's got to be a physical change rather than a chemical change. Okay. Okay. So any questions about this part? How to look at an equation that's given to you, and from that equation determine whether it's a physical change or a chemical change, even though you may not know what that chemical is, right? Because you're looking at the reactants, which is to the left of the arrow, and then you're looking at the products. And if you can see, you see a plus symbol on the right-hand side, that's a good indication you got a chemical change because you created 2 or more different products, which now means that you completely change the formula for the starting material. Okay, I'm getting 3:40, got 20 minutes left. Well, all right, well. Let's talk about a little bit about the elements themselves, okay? Now, and the compounds and mixtures and how we define what is what. Element is one type of atom itself. All right, just one type. We have in the periodic table a number of elements. Okay. Now you can't break down the elements any further into other elements. They are what they are. I get an element, if I break it down any further, and then I'm breaking it down into a proton or electrons, which is a totally different thing, okay? So it's element is the lowest level that you can go with respect to elements, as compared to a compound. A compound, by definition, is made up of 2 or more different atoms bonded together, okay? H2O, hydrogen and oxygen, made up of hydrogen element and the oxygen atom. 2 or more different elements create a compound. Now I can take that compound and treat it and break it down to the elements. So I can take water, H2O, and break it down and go back to oxygen and hydrogen, okay? Whereas I can't do that with the element. The element is the lowest level I can go. So a compound can be broken down further back to the elements, okay? Pure, well, it's pretty self-explanatory, consists of that item itself, whatever it may be. It could be a pure compound, it could be a pure element, right? Or it could be a mixture. A mixture could be, 2 or more different compounds, or a combination of an element in a compound, or a combination of elements, okay? It just, as long as they're different species, just a mixture. So if we look over here to matter with the flow chart, if you go to the right, a mixture is depicted on the far right. You can see here the red colors and the dark. Right here, let me draw this real quick. If you look at this, notice these 2 red spheres. Okay, they're together, okay? They're the same color, same size, more likely the same element. In fact, there's a specific name for that type of element when there are 2 of them together. They're called diatomic. We're going to learn about that here in a bit. And so we have an element, and then in the red color, and then we got elements that are not diatomic but singular in the dark color. So definitely this is a mixture of 2 elements, okay? We look at the next picture, looks like we got 3 different elements. We got that bluish green color element, we got the red and the dark. So it looks like we have a mixture of 3 different elements. Now, with respect to pure material, okay, sodium chloride here on the far right, you have a sodium ion and a chloride ion in the solid form attracted to each other. Okay. Then we have a compound. Both of these are compound, be it H2O, be it sodium chloride, because they're made up of 2 or more different elements. So you look at the Mickey Mouse ears here on the bottom. The yellow represent the hydrogen atoms, and the red represents the oxygen. Okay. And then pure material. Here's an example of a diatomic, meaning 2 elements together. Okay. Or monatomic, meaning just an element all by itself, which is atoms. But the diatomics are called molecules. All right. So examples of mixtures. Well, metal alloys, there's a good example of a mixture. For example, 18 karat gold. That's not 100%, or even 24 karat gold. Very rarely do you find jewelry out here made up 100% pure gold, simply because it's not very practical. Pure 100% gold is very soft, and it doesn't lend itself well to be hard enough so it can survive the elements of banging and so forth before it gets disfigured. So they generally put in other elements in it to give it a little strength. So they make what are called alloys. Okay. Sand, graphite, tap water. Tap water is definitely a mixture because it's a mixture of all the different ions that are in water. Tap water is not 100% pure water. Okay. And of course, the air around us is a mixture of different gases. You can have pure sodium chloride salt. Okay. A diamond, not a lot of diamonds are 100% pure, but I'm sure there's some out there. Diamond is something interesting about a diamond. First of all, they're made up of carbon. Okay. And what's mind-boggling, think about this, carbon can be made, a good example of carbon would be like graphite. Graphite, sometimes they use it for pencils. They use it for dry lubricant. Okay, very soft, slimy material. Okay, whereas a diamond, the hardest material on earth. Now, be it graphite, be it a diamond, carbon is still carbon. Okay, they both are carbon in both examples. But the question is, why is it that carbon in diamonds is configured in such a manner that is the hardest thing on earth, whereas the carbon in graphite is configured such that it's not? And it's just a matter of how the atoms are put together relative to each other. The configuration of the carbon atoms in the diamond make it very hard compared to the configuration of carbon in graphite, which is more of sheet form, make it very slimy. Okay. Anyway, very, very fascinating how you can play with the configuration and totally change the properties of the same element. All right, distilled water is a compound because H2O. And is distilled, it's classified as pure because you heated it up and got it as clean as possible. All right, here's some diagrams. Okay, we're big on diagrams. So we have the element, which is shown on the left. Okay, it's a good example of an element, specifically what is called the diatomic element, because the 2 spheres are hooked up together. That's how they're traveling. Okay. And then in the middle, you got a compound. You got something that's gray, 2 grays, and 1 white in the center. Generally, you learn that when we start learning about how to put the compounds together, you're going to find 90% of the time that you're going to have a element that's in the middle. That's the central atom. And then everybody else is bonded to the central atom. So if you look at that compound example, you have the white sphere, that's the central atom, and then the gray ones are bonded around the white. Okay. On the right side is a mixture. Looks like we got a mixture of two elements and a compound. Okay, A is a good example of diagram of an element, okay, specifically diatomic. B is an example of a compound where you have two or more different elements bonded together, okay? Now, these are models, and I'm not saying this is the way these compounds look. These are models because to allow us to put in our brain a picture of how things are put together. Yeah, these are models that we utilize, to help us visualize the chemistry involved. All right, C is a mixture, specifically of two different elements. D looks like it's pure; it's all one color, okay, of an element. Whereas Z again is an example of a compound, and F is a mixture of at least two compounds and an element, diatomic element. And then G is a mixture again, compound and element. And then finally H is basically just an element. That's it, very ordered, very structured, suggesting that it's a solid. Okay, let's shift gears for a little bit. And let's talk about the elements, okay? Each element has a very unique name, symbol, and number. Oh, I meant to do this. Okay, because if you look at the elements here, there's 118 elements. Now, above the letter is the symbol for that element. Above the lettering is a number that goes from hydrogen over here, which is a 1, to number 118. Okay. That number represents that atomic number for that particular atom. It's a very unique atom. Okay. Then underneath that symbol on the product table is another decimal number. That is the atomic weight of that particular element, which we're going to utilize in doing calculations down the road. So that's the atomic weight. Now, a word about atomic weights. Strongly 100% ask you to use atomic weights on the product table. And this is why. Because Canvas is definitely not AI technology. All right. And so you can get on the internet and get the atomic weights, and you can get atomic weights from a number of multiple decimal places. Okay. And then you use those in the calculations, and then your number could be slightly off by 0.01 with respect to Canvas. And Canvas being that far off would treat it incorrect, okay? So, but if you maintain our atomic weights here, that should not occur, okay? But either way, if you use someone else's atomic weights and your number was incorrect, even though you're only off by 0.01, please send me an email. I'll definitely look at it. We'll give you credit for it. But to circumvent all that, just use these atomic weights and you'll be okay. All right, so most of the elements have one symbol, like C for carbon, H for hydrogen, okay, but some of them have two letters. What's important here is that second letter has to be lowercase, okay? So Ca is calcium, Co is called cobalt. If you write it uppercase, C uppercase O, you no longer have cobalt. You now have carbon monoxide. Okay, so make sure if you're talking about cobalt, and it's C, capital C, lowercase o. if you're talking about carbon monoxide, both C and O are capitalized, okay? So it's very important. Now, most symbols have English names, so we got hydrogen for H, okay, oxygen and helium respectively. But some have Latin names, like PB is lead, okay? It's called, comes from plumb. And then AU from Orium means golden dawn. Okay. Be familiar with the first 20 elements, and we're gonna run through that real quick. When it comes to, Christina has a question, we're only required to round 2 decimal numbers. Use the 2 decimal numbers from the periodic table. When it comes to rounding, it's a totally different ballgame. We have a whole chapter in rounding numbers out, doing sig figs. And generally, the atomic weights don't play a role in that, okay? So yeah, just use the 2 decimal places from the periodic table that we supply. All right, let's do the first 20. All right, so we start with hydrogen on the far number 1, that's H, hydrogen. Shoot across to He, that's helium. Li is lithium, Be is beryllium, B for boron, C for carbon, N for nitrogen, O for oxygen, F for fluorine, Ne for neon, okay, Na for sodium, Mg for magnesium, and we should have question number 13. Good old Al for aluminum, Si for silicon, P for phosphorus, S for sulfur, Cl for chlorine, Ar for argon, and 19 is K for potassium, and then number 20, Ca for calcium. Now, we're going to introduce more as we go along, especially these metals in here like Fe for iron and so forth. But for right now, we stick to these. So we got Ag, which is silver, Au, which is gold, Pb is lead, Br is bromine, I is iodine, and Hg is mercury. Okay. Now, the physical states for these elements at 25 degrees and at what we call normal atmospheric pressure. This is normal atmospheric pressure. 25 degrees. We have to speculate, not speculate, but state what temperature we're at. Because obviously, you know, the boiling point, water at 100 degrees is gas, right? Right? Water at -10 is solid. So we have to be very specific. So at 25 degrees in one atmosphere, okay, there are only 2 elements that are liquids, and that is mercury and bromine. Okay. With respect to noble gases, we have H2, N2, O2, F2, Cl2, hydrogen, nitrogen, oxygen, fluorine, and chlorine, which are gases, 1, 2, 3, 4, 5, plus what we call noble gases. Well, what are noble gases? Well, that's where I send you to the periodic table. On the far right, right here. These are called noble gases. So we got 1, 2, 3, 4, 5, 6, and 7 noble gases. Okay. Those 7, 8, 9, 10, 11, 12. So we got 12 elements that 25 degrees are gases. 2 elements at 25 degrees are liquids. So that means that all other elements at 25 degrees are solids. Okay, and this here kind of shows you. So the two liquids, that's a metal, mercury and lead and bromine are liquids, okay? The ones in yellow are gases, okay? And then what's in blue are all solids. Okay, so you should be able to just looking at the periodic table and pick out and say, okay, oxygen, is oxygen a liquid, gas, or solid? Knowing its position in the periodic table, you can automatically say, oh, it's a gas. Okay. And potassium. Potassium is a solid right here at 25 degrees. Now, I mentioned the term diatomic. That means those are two elements that do not exist, cannot exist by themselves. They have to exist with a partner, okay? And we call that diatomic. They're bonded together like the two, like right here. You can see how they're shown here together, like so. Diatomic. Of the 118 elements, there's only seven that are diatomic. We got hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Okay. One way to remember that is have no fear of ice cold beer or beverage. Okay. The B is for bromine. The C in code is for chlorine. The I is for iodine. O above is for oxygen. F is for fluorine. N is for nitrogen. And H is for hydrogen. Okay. So there's only 7 elements that are diatomic, and we need to learn that they're diatomic because down the road, when we start writing chemical reactions, it'll be given in words, the reaction of oxygen gas. And we have to remember oxygen is diatomic, so to write the formula of oxygen, it would be O subscript 2, okay? O subscript 2. Make sure it's a subscript. It has to be a subscript. All right, got a couple more minutes. Okay. Elements are broken into 3 parts. They're either going to be a metal, a non-metal, or a semi-metal, or something that's metalloid. Okay. And we can use, again, the periodic table to determine whether something is a metal or metalloid, just based on their position in the periodic table. This is also important because we're going to learn that metals, put this in long-term memory, metals lose electrons, okay? Long-term memory, lock it up in there. Non-metals gain electrons, right? So when metals lose electrons, they end up with a positive charge. When non-metals gain electrons, they end up with a negative charge, okay? So semi-metals, we're not going to work a lot with semi-metals in this class. Okay, but all semi-metals are just elements that have properties of metals and non-metals. It's just like a mule. A mule is a combination of a donkey and a horse. It's got properties of a horse, properties of a donkey. Okay. Okay, so non-metals are located on the right side of the stair step. Semi-metals are touching the stair step. And then metals are on the left side. So what stair step are we talking about? And it's this one on the periodic table. All right, so if you start here in green, you start with boron, you go to silicon down to Ge, go across this way, go down this way. So right there. 117, we're not sure yet whether that is a metalloid. We suspect it probably will be, but we'll learn more down the road. Right now, those are the metalloids. So everything to the right which in the reddish color are the nonmetals, including hydrogen over here on the far left. That means that everybody here in blue are metals. Okay. So if you look at the periodic table, you can see that little crisscross, that stair step to tell you who the metal, where the metalloids are. So you can, at a glance, say, okay, if you're asked element 104, is that a metal or non-metal? Well, we look for it, 104. Okay, find out where it's at on the periodic table and say, hey, it's a metal. Okay. Element 35, well, it is a non-metal. And you know what? We're going to be done with this. Give me like one more minute of your time and I think I'll finish it. All right. So metals are shiny in appearance, pretty self-explanatory. We can smash them up all we want, put them in different forms. All of them are solids except mercury. Mercury is the only metal that's a liquid. Density is usually high. The melting points are usually high, okay? And they're all good conductors of electricity, hence good conductors of heat, compared to nonmetals that generally have dull appearance. They're brittle solids. Many of them are gases. Their density is usually low melting points, poor conductors because they don't conduct, and they won't conduct heat very well, so they're better insulators than they are anything else, okay? So I think it's the last one. Be able to look at the periodic table and determine what the name for at least 20 plus the other metals we gave you, okay? Determine whether it's a solid, liquid, or gas. Any of the elements, 118, depending on their position. Determine whether it's a metal, non-metal, or semi-metal, again, based on their position on the periodic table, okay? And determine whether it's diatomic or not. And there's only 7 of them that are diatomic. Have no fear of ice cold beverage. Okay. And that, ladies and gentlemen, ends chapter 1. We're on the road. All right.